All right, everyone, we're going to go ahead and get started. Thanks so much for being here. We've got just a couple more people coming in, but my name is Cinnamon, and I'm going to be your host for this event. And thank you so much for being here for our afternoon seminar. There's some new faces in the room, so I'll talk a little bit about some logistics. This event is a hybrid event, so we have folks online and folks in the room. That means that if you're online, please put any questions you have for today's speaker into the chat box. And our helper here, Katie, will make sure that she reads those out or addresses any of those issues, especially if you can't hear me right now. Let us know, please, so that we can fix that before we get started. For folks in the room, if we get to the question and answer section and you have questions, just raise your hand. I'll bring you a mic, and that way folks online can engage with your questions as well. And again, just thank you so much, and thank you everyone for signing in. I appreciate that. It just helps us, as I told many of you, buy cookies and coffee, and it's not just for me, which is good. Okay, I have a couple of quick announcements to make. So next week's seminar is already May 1st, and it's a special one for us because it is our student invited speaker, Kyle Elliott, who's an associate professor from Canada's and McGill University. So he will be discussing seabirds as an indicator of environmental change. And Kyle was chosen by our students because they felt he would resonate with this community. So I'm hoping that you all come back and learn a little bit more from Kyle. So same place, same time, May 1st. And if you're interested in any of the Hatfield events, you can go to the HMSC homepage, go to the events page, and you'll be able to find all the information about all the different events that we have here at Hatfield. But I want to quickly hand this off because we're excited for today's speaker. And today's speaker was invited by Bob Ziak from PMEL. So I'm actually just going to hand the mic off to Bob, and Bob can introduce.
Thank you. Thanks, Cinnamon. Hello, everyone. Welcome. Really appreciate you coming out. It's my extreme pleasure to introduce Pierre-Yves Raumer, PhD candidate from the University of Brest, Occidental in Brittany, France. Pierre is from Quinton, I think is your hometown. And he has a bachelor's and master's degree in computer science from the University of Rennes in France and the University of Milan in Italy. He's going to talk today about his research using hydrophones or underwater microphones to record volcanic eruptions on the seafloor in the Indian Ocean. And with that, I'll say, merci.
Oh, yeah. Thank you very much, Bob. I don't know if you hear me very well. I think so. I wanted to start this presentation by thanking Bob because he welcomed me. And despite these very particular times that NOAA is facing, we can say it, he managed to find some time every day to talk and discuss with me. And that was very nice. And also thanks to all the people that made this stay a bit more pleasant. That being said, let's start. So I'm going to speak about ridges, mid-ocean ridges, about a project that was started in my lab regarding ocean ridges in the Indian Ocean. And I will finish by speaking about my favorite topic, which is myself, and a bit of, in particular, a bit of my work. So to start, we all ask ourselves at least one time in our life, what is an ocean ridge? That's a good question. Ocean ridges are actually like a sum of observations. They are observable stuff in the ocean. And the first thing we can say about them was discovered 150 years ago. So there was a Royal Navy corvette called Challenger, HMSC Challenger, that performed the first oceanography cruise of history. And they actually performed a lot of bathymetric survey. So how do you do that at this time? So to measure the depth when you're in the 19th century, they were mainly using plumbing lines. So the idea is fairly simple. You just put some plumbing line in water, and when it reaches the bottom, you know how deep it is. And at this time, they had, of course, good equipment that you had mechanical winches to make it easier. So they did it several times, like you get at the ocean bottom your plumbing line, you note the depths, and you do it again and again and again, which is very long. But in the end, they discovered something weird, in that in the middle of Atlantic Ocean, you have a kind of mountain, a big mountain. Nowadays, we have a clear view of the bathymetry of the world. Well, clear, that's pretty much clear. And with such maps, we can easily see that indeed you have this kind of snakes in the middle of oceans, which are actually ocean ridges. It's not always in the middle, but nearly. And so this is the first observation we can make. There is a second observation that was made some decades later, is that Africa and America seem to fit pretty well, given their shapes. So from that, some people said they may be actually a kind of extension, that there is a spreading. And it seems that ridges are in the middle of the spreading. So it's not completely random. It should be a kind of process around these ridges. We don't know which, but that being said, another observation a bit more complex that we can do is about, well, let's take North Atlantic Ocean. If you take a look at what you have in the middle of this ocean, so that we speculate to spread, you have some rocks near the axis. So rocks at first glance can seem uninteresting. However, it carries a lot of information with them. So actually, the idea of basaltic rocks near the ocean bottom is that they contain, most of the times, rocks called magnetite. And when rocks actually solidify, so they are lava at first and they slowly solidify, you first have kind of tiny shards that appear, and these tiny shards orient themselves towards a magnetic field. When the rock is completely solid, these magnetic shards are fixed, and they remain such for, well, the rest of the lifetime of the rock. And so when you actually get rocks, when you study them, you can try to guess how was the magnetic field at the time of the solidification of the rock. And doing that on a wide range around the ridge axis, you can actually observe something. It's that you have a change of polarity. You have like a north-south magnetic field in the middle of the ridge. And if you get a bit closer to a border of the ocean, you have the magnetic field that swaps over a distance. In the same decades, humanity discovered that the magnetic field of the Earth has actually changed a lot in history. And it's quite easy to make the link between both. That is, when the rocks solidify, they align themselves towards the magnetic field of the Earth. And given the chronology of magnetic field change, we can try to estimate the speed of propagation of the rocks. So for example, Atlantic Ocean is spreading at a speed of roughly 1 inch per year, which is quite not much. It's a slow ridge, but it's an average speed. From that, you can even speculate that you have a kind of plates that are separating on each side of the ridge. And now we have a much clearer view of the age, thanks to this phenomenon of the oceanic crust all over the world. So you can make maps like this. And when you see the age of the rocks, it is very consistent with the view where you estimate that the ocean crust is made at ocean ridges and it's spreading with some speed. So all of what I said actually happens over millions of years. That's spreading of the ocean crust. You don't expect to witness that in your lifetime. However, ridges also produce events that we can monitor in our lifetime. These are seismicity. So if you take a look at the map of the seismicities that were recorded by seismometers in the last 60 years, you clearly see the ridges, which means they produce a lot of earthquakes all the year. And this is the last observation we can make about them, which is quite easy. We actually started a project, so in my lab, that is GEODAMS, I will speak about it, that focuses on short timescale expressions of ridges, so mainly seismicity like this. And to understand a bit more how it's made, we have to go a bit deeper in the modeling. And to do that, we have to speak about sneakers. So if you put some sneakers in a fridge, for example, and after that you take it and you pull on each of its sides, you have a kind of stress that appears in the middle of the sneaker, and you expect it to break down. Like it breaks in 2 pieces. On the opposite, if you let your sneaker under the sun for a couple hours, you don't expect it to break so easily. It will actually deform itself. And it will, this way, accommodate the stress you can apply to it without breaking. So rocks behave mostly like sneakers in a way. If you get to the ocean bottom, rocks are hard, they are brittle, that is, you cannot bend them. And if you apply an extremely huge stress on them, they will end up breaking. On the opposite, if you go deeper and deeper, at a point, your rocks are getting very warm, and getting very warm, they can bend themselves, they can deform themselves, and they are, as we say, ductile. And we usually use these properties to divide the ocean floor in two layers, which is lithosphere and asthenosphere. So lithosphere, lithos for rocks, and asthenos for wick, I think, something like that. So asthenosphere contains a bit of magma, but a very little bit, like less than 1%, as we estimate. And mostly, so it's soft. It can a bit bend itself. And over large time scale and space scale, you can expect it to behave a bit like a fluid, like it can have internal currents. And given that the bottom of the asthenosphere is much warmer than the top of the asthenosphere, this automatically creates a current like convection. Like if you put a heater in some room, it will happen with the air too. And so this is a very rough approximation of what actually happens, but it works. It works quite well as a model view. So asthenosphere has a kind of currents in itself, but lithosphere cannot follow this movement because lithosphere is strong. It cannot deform. And so you have a stress that is increasing in the middle of the lithosphere. And at a point, this should trigger some kind of break, like the cold sneaker. So in particular, you have two ways for the lithosphere to accommodate this stress that we give to it. The first way is that it can break in the middle. So it can break in two, and you expect then some magma to fill the hole. And this is actually an eruption. On the other side, you can also have off-axis normal faults that appear. So they are called normal fault. It's actually oblique breaking. And you both have a vertical and a horizontal movement thanks to this kind of fault. So there is the plate is slipping on itself. And this enables to accommodate a bit of the traction inflicted by asthenosphere. So basically, if you have this kind of folds that appear, you have some vertical movement too, as I was saying. So it means you have a kind of hill that appear near the ridge. And over time, as you have more and more eruptions in the middle of the ridge, this normal fold, this new hill, is going to get a bit far from the axis. When it's far enough, it's not activating anymore, and you expect a new normal fault to appear. And so this is an endless cycle that creates a lot of normal faults one after the other, which we actually call abyssal hills. So if you take a look at how the bathymetry of Central Atlantic Ocean looks like, you have a lot of hills, and these are a lot of normal faults created one after each other. So it's a kind of factory of hills that never finishes. And one small thing also we can add just to have a complete view of the faults in a ridge, or over a ridge, we have another kind of fault that is pretty common that we call transform fault. So if you look like how a ridge looks like this one, it's not a straight line as we could expect. There are a lot of discontinuities, and some of them are actually faults that slip, and we call them transform fault. Well, just I don't go deep into details for this, but that's useful to know it. That being said, so as was said before, to accommodate the movement of asthenosphere, so lithosphere has mainly two methods. So there is a tectonic activity, which is the faults, so the normal faults I was speaking about, and the break in the middle, which is magmatic events. Actually, normal faults, when they move, when there is a slip near the axis, we know it makes, in most of cases, earthquakes, and it's what we can monitor with seismometers. But it may sometimes produce a kind of slip without an earthquake, that a slow slip that happens softly, and so nothing is shaking, or nearly. We are not sure of that. And if so, we focus on the short time scale of how a ridge expresses itself, like the observations we can make on of ridges. We still have a lot of questions unanswered that we don't know, we don't have a clue of the answer of these questions. And so it was the goal of the project GEODAMS to at least give insight about some of them. So here comes the project GEODAMS. It's involving quite a lot of persons from mainly French labs and also Geo-Ocean in Germany. So the idea of, just quickly, so the leader of the project is Jean-Yves Royer at the right hand corner, and at bottom left you have Jean-Arthur Olive, which is the second leader of the project. That being said, the goal of the project was to first find a ridge, a convenient ridge to monitor, and then to come close to this axis with some research vessel. So the research vessel that was used is a Marion Dufresne, which is around 300 feet. So it's quite a decent sized vessel. And thanks to this vessel, there are a lot of operations to perform to monitor the ridge. The first operation we do and we did is the bathymetric survey. So thanks to sonars, the idea is to well, just sound the bathymetry around our area to get an idea of the morphology of the ridges and what's up there. And then there is the deployment of many sensors. So the first sensors we deploy are acoustic beacons. The idea of these acoustic beacons is that they are big tripods. On top of them, you have this pink piece here that is an acoustic emitter and receiver. So with that, two acoustic beacons can discuss actually, and they can measure the distance that separate them. And if you do that for a lot of acoustic beacons, you can have a clear idea of how things are moving horizontally. In addition, so there is a pressure sensor called A0A. I will speak more about it. The idea of a pressure sensor is that it measures pressure, of course, and pressure is directly related to the amount of water you have above your head, which depends on two factors. The first being the height of the ocean, like tides and swell, but this does not interest us. And secondly, you have the movement of the ground itself. So ground can inflate or deflate depending on what happens. For example, if there is an eruption, you expect a deflation, but that may change. Then we have acoustic sensors. So the first one being an hydrophone on a mooring line, and that stays there for 4 years. And the second, a glider that we deployed for around 10 days. So the goal of the glider was mainly to monitor the biological activity. So that's why it's close to the shark here. While the hydrophones on the mooring lines are here mainly to monitor the seismicity and eruptions. And I will talk about them later because it's my business. And a last sensor that was deployed, but not the first year, but the second year of operation was OBS, so ocean bottom seismometer, which are there to monitor the seismicity. Okay, so the area that was chosen is this one. It's Southeast Indian Ocean ridge, called Seir, and it's close to Amsterdam Island. So this is a tiny island that is quite isolated, actually. But this island is French, and there is an occupation for scientific activity. And as such, there is this large vessel, the Marion Dufresne, that goes nearby once a year, twice a year, sometimes more. And the idea was to use these regular cruises to deploy our sensors and recover them. If we take a look at how it is, we focused on this area. The ridge, as we can see on the set map, it's not that clear, is going from southeast to northwest. So it's kind of oblique ridge. And so in our area of study here, the red dotted line is actually the ridge axis, while the black dotted line is one of these offset I was speaking about before, so transform fault, that is sleeping on itself. If we make a zoom, so this is quite ugly because it's the resolution we had before coming, before we made bathymetric survey. It's what we had as data to know how it's made. We made 2 networks of sensors. So here are acoustic beacons, so the 3 pods things. We had one network made over the transform fault, northern part, just to see if the transform fault is faulting. And a ridge network that was made across the ridge axis to monitor how it was going to spread and this kind of stuff. If we take another view of this area, just to get a head edge, because this one is an oblique projection, so the north is not at the top. We actually added 5 hydrophones to this network. So these are the 5 stars you can see here. 4 of them worked, and the last one, being the west hydrophone, didn't work due to some card failure. Okay, so to speak about the acoustic beacons again, that we call Canopus, it's their commercial name because it's a company that makes them. So the idea is that they monitor the distance between them. So for example, A monitors the distance between itself and B and C. And if you have some movement like this, like C and B are moving, you expect the AC distance to increase and the AB distance to decrease. And actually, if you have a network of such acoustic beacons, not only 3, but like 10, 11, or something like that, you have a lot of pairs of stations. And each pair of stations gives you information of how it's actually moving. This is our lot of equations, and inverting that, you can have an idea of how is the displacement field around this area. That is how stations are moving, in which direction they are moving. So that's a lot of physics to make, but that's, you can do it. So it's how they look in practice. So they are quite tall, as you can see, because I don't consider myself as a small person, and it's myself. And you put them in the ocean bottom, as in the right part. Which can be sometimes a problem because near ridges, we expect the area to be particularly steep, and we want our sensors to remain vertical. So there is a tilt sensor in it, and to get well, the orientation of the sensor, and we had many times to deploy them again and again until it was vertical. That being said, this white box is our pressure sensor. So it's like a normal pressure sensor, but more expensive. Not just to show that we have money, we don't have particular money, but the idea is that most pressure sensors actually drift a lot. If you let them alone in the bottom of the ocean, after some months, you expect them to lose a bit their calibration. So they will still speak something close to the reality, but what they will tell you is a bit erroneous. There are some mistakes. While this pressure sensor, A0A, has a void chamber inside itself, and from time to time, the pressure sensor looks at the void chamber, it measures the pressure, and it knows it should be 0, so it calibrates itself, and it goes back to the external side. So this makes it more expensive and mostly more accurate. As we can see on the right part, there is this red line, that is what a pressure sensor measures without correction, and the green line is when you correct it. So you expect the curve to remain flat, horizontal, and it's still not perfect, but we're getting something better. When we want to measure vertical movement of the order of the millimeter, we want very good calibration, and we don't want a big drift. So hydroacoustic now. So we put hydrophones and glider, as I was saying. The idea is that in the ocean, you have a lot of hydroacoustic sources. So that ranges from icebergs, can crack, you have whales that sink, you have human activity, and most importantly, in our case, volcanoes and earthquakes that make a lot of noise when these events happen. Here is how it looks like in a whole year. So this was a station moored near our area, but some years before. So this is a spectrogram over the whole year. For people not knowing it, spectrogram is like on x-axis you have time, on y-axis you have frequency. And if you have a pixel that is bright, so bright on this color map means red, it means that at this time and at this frequency you had a high signal. So on this spectrogram over the year, you can see many things. For example, you have vertical peaks. Vertical peaks are mainly seismic activity. That is because over a short time scale, you have many broadband signals, and you expect them to be seismic crises. And you have horizontal bands, which are actually biology. So yeah, I see the formatting isn't well. Biology, you have mainly large whales because at our frequency range, we only have large animals that we can hear, well, mostly. And they actually sing to breed, most of them. And singing to breed, they emit some stereotype signals. That is, they always look the same, that always the same frequency, a bit like many birds actually. And if they are singing to breed over 6 months, for example, you expect a 6 months bend on your global spectrogram. So, for example, near the letter B, you have a large horizontal bend near 20 Hertz. These are a mix of Antarctic blue whale and field whales that sing at this frequency. And from that, you can say they are breeding in the winter season, yeah, which is what we expect. Yeah, because the southern hemisphere, it's winter. But anyway, whale in our case, we study them because while hearing them, it would be a pity not making studies about that. But these are not the first goal of the experiment. So here is how it looks like. Our hydrophones are put in buoys, orange buoys, like this one at left. And we have the glider. So gliders, it is a bit missile shaped in a way. We just put it overboard on a small workboat, like the one on the right. And it does its job for 10 days alone. So here is the timeline of our experiment. It started actually 1 year and 3 months ago, so it's quite recent. We deployed nearly everything except the seismometers that were deployed 3 months ago in 2025. In 2028, we expect the experiment to stop. Actually, it should be, we should recover everything and go with it. But something unexpected happened. Actually, only 3 months after the deployment, first deployment, we had a big, very big earthquake crisis. This actually is a kind of earthquake crisis we only expect to see once a century on a particular segment. And we had the luck of observing it just 3 months after the beginning. So I can say we are quite lucky. We could know it because, of course, the sensors were underwater at this time. So it was not possible to get their data before 2025, but seismic stations from Indonesia, Australia, Madagascar, or other places recorded many earthquakes, and this made a lot of earthquakes in international seismic catalogs. To be more precise, we had 59 events in our area in only 2 days in our area of study, which is quite huge because ridges are making very small magnitude events, and moreover, seismometers are very far from them, so you only expect them usually to detect a small amount of earthquakes. So 59 is great. So from when we observed this in the beginning of May, we couldn't wait to go to our next cruise to get our data, which is what we did some months ago. And the first thing we did was a bathymetric survey to see if something changed. And we were surprised to see that we had up to 100 meters of vertical difference between what we measured last year and what we measured this year. So that's quite a lot. If we sum the volume that this may represent, this may be close to 1 billion of tons of new rocks between last year and this year, which is a decent sized eruption, we say. So if we make a synthesis, we, thanks to the MBS's multi-beam echo sounder, so thanks to the bathymetric survey, we knew that there was new material. And we also used our other sensors, which all recorded in their own way the crisis. So we have acoustic beacons that measured up to 2 meters of horizontal distance increase between them or decrease at some areas. So they had a tiltmeter, remember, to know if they are well deployed. This tiltmeter changed of up to 15 degrees for some stations. So one of them nearly fell even. And we also measured an increase of 0.6 Kelvin for the closest station because they have an integrated thermometer. So 0.6 Kelvin may seem quite small, but if you have a large volume of water heated by 0.6 Kelvin, it represents a tremendous amount of energy. We also had our pressure sensors that measure 2 meters of subsidence. So if you remember, we had this drift consideration to measure change of vertical position on the order of some millimeters. And so in our case, we really didn't need that because we measured 2 meters of subsidence, which is much more than what we expected. And so we have our last sensor that monitored it, which is hydrophones. And this was a bit my business because it was my job in this campaign was to help at the operational stuff and to treat the acoustic, hydroacoustic data, which is what I did. So first of all, here is how it looks like if you make the spectrograms of the whole year of study. So you mainly see the same observations that we had with the previous spectrogram of another year. Like you still have the same whales, which is a good thing, you know. And mostly we have this peak, which is the crisis. It's the end of April 2024. But first of all, we could ask ourselves, how is that we hear earthquakes? Because when an earthquake appears somewhere, so if there are seismic waves propagating in the crust, basically the ground is shaking. And these waves make the ocean bottom shake. And there is an area over the earthquake where you expect this shaking to produce sound, so acoustic wave. So over this area, acoustic waves are created, and they can propagate over very long distances with very low attenuation, thanks to a particular channel of water column that we call SOFA channel. And we can then detect them with our moored hydrophone. So we do that. And this T-wave, as we call them, look like this. So it's how you may expect to see an earthquake on a hydrophone. So here, as we say, you have a P and a T wave, but just see that this is how it can look like on a spectrogram. So it's what you have to look for when you are chasing earthquakes on acoustic data. So what I did in the beginning was to pick some of them. So I browsed some days of data, and I was looking for this kind of signals because we know these are earthquakes. And this enables to make a histogram of the number of T-wave per day. And what we see is that you had a maximum of events on the 27th, and then it slowly decreased until the 2nd of May, where we can suspect this is the end of the crisis. On the 26th, the events started at 8 p.m. So they are a smaller activity than on the 27th, but actually it's denser because you only have 4 hours of them. If you pick your T-wave on at least 3 stations, you can, using the difference of time of arrival between each station, you can try to locate the signal of origin and make a map of it. So you get some points on maps like this. And this is interesting because we can see that at the beginning of the crisis, so it's the black dots here, your activity was only located near the axis. It was very close to the ridge itself. Then a couple of hours after, starting from 2 hours from the beginning, it began to spread. You have some activity at the northern part, which is a transform fault. You have activity at the southern part, which is another transform fault. And at west, which are actually old normal faults that we supposed to be inactive, but that may be activated by the shaking in the middle of the ridge. That being said, if we make a focus on this area, so in the 2 first hours of the crisis, we can plot the evolution of the position of your earthquake in function of time during these 2 first hours. So this gives something like that. The first observation we make is that events actually crossed the network of stations, which are the crosses here. So a station just saw something coming by, and well, they escaped. No one was harmed here, which is a good news. And we can see that there is a kind of propagation that is even start in the bottom part here, and they progressively go towards the top part of the graph. So it means they are propagating along the axis, and we could think it's a kind of dive propagation. That is, when magma is reaching the ocean bottom, it's propagating under the ocean floor before finally reaching seawater. who says difference of position in function of time, says speed. And so we can try to estimate the speed of this dike, which I did with Monte Carlo. I spare you the details, but I ended up with the conclusion that there is a propagation speed of around 1 meter per second of these events. Then I asked myself, could there be more events later in the year? The thing is, I didn't want to pick events over all the year because that would be a big job. I'm quite a lazy person. In my PhD, I developed tools to automatize the detection of earthquakes, and it's what I applied. So here is this tool. It's called TISNet. I spare you the details too, but it's a neural network. The idea is fairly simple. You have acoustic data as input, as you treat them as a spectrograms, and as output, it says you when you expect to have earthquakes, like dates of detection of earthquakes. It says here you have a T wave, here you have a T wave, and this makes a kind of time series. And with that, you can. So I did apply this tool on the whole years of data on my 4 hydrophones, and this gives 4 graphs of. Yeah, you can see the amount of T wave in function of year. We see a kind of peak in the left part, but this is very noisy, which is April. But it's normal because hydrophones are victim of their success. They are so efficient to monitor seismic activity that they can detect T wave from nearly all the Indian Ocean. And the result is that they have a lot of earthquakes every day, all the year. And well, this is noisy. So I developed another technique to associate, as we say, earthquakes from different stations. So from the 4 stations we have here, to them filter them by the area of origin, of source. And I filtered these events by our area of study to get only the T waves that originate from our reach. And this gives much more, well, it's clearer, I would say. We clearly see our crisis here in April, and it doesn't last long. Then there are no T wave left, and you have a small peak, some like 2 months later in June, and some small peaks in the end of the year too. I took a look. It seems that the peak in the end of the year are not related, but the one before come from our area clearly. Okay, and so I made a small zoom just to make the same histogram I did before when I picked manually some events, just to check that my automatic method was actually working. And we have clearly the same observations that we did before. So the conclusion was that my automatic tool works, and I managed to replace myself with a machine, which is good. So we could have stopped there, but there is another kind of signal that interested us. When magma reaches seawater, it actually generates an impulsive signal, that very short signal that is broadband. We are not sure how it is generated, but it is generated. We observe it. And this looks like them. It's not very easy to see, but you have a lot of vertical peaks. And well, we call them impulsive signals in my lab. And it should be interesting to monitor them too. So I began again. I did some manual picking of some of these events. And I observed exactly the opposite as for the T wave, that it's not decreasing, but increasing in the first days. So I wanted to know how when it stops. And same idea, I couldn't pick everything myself. So I adapted my tool with the events I already picked to train a new model, which could be able to detect those impulsive signals. It works. I do the same. So I get a histogram for each of my 4 stations. We clearly see our crisis in the top stations here. Well, in the bot stations, it's quite hard to see, especially in the bot left one, which is the south station that nearly didn't detect those events. We don't know why, probably because of bathymetric shadow. So I used the same technique. I associated these different detections from different stations. This enabled to filter them by location, and this gave me a much better histogram. We see an increase in the beginning of the crisis, then it's brutally decreasing, it's increasing again, and it's finally finishing in June 14th. But remember, it's quite interesting to see that at this precise time, we had our small peak of T wave of earthquake activity. So this may be linked, like the impulsive events are stopping, and then you have some earthquake activity. And this enables to make a lot of conclusions, I would say. But first of all, we could also localize precisely our impulsive events. And if we make such a map, we can see that there are two clusters of impulsive events. But now I cannot explain it. I don't know why. I just wanted to show it because I think it's beautiful. That being said, the last observation we can make is to compare histograms from earthquakes and impulsive events. If we do that, we clearly see indeed there is a kind of complementarity. The more T wave you have, the less impulsive events you have. This could be explained because impulsive events are caused, we think they are caused by contact between lava and seawater, while T wave are caused by earthquakes. And at the beginning of a volcanic crisis, you have kind of extrusion, like the magma needs to make its path to reach the surface. At this particular time, it's generating a lot of earthquakes. But when it's finished, when there is a clear path to flow, it may be a bit calmer, I would say. And this may be a reason or not. So we can make from this observation some guesses. I can make some guesses, but I'm not a geodynamician, so this won't be a very high level. But still, I can guess that the dike propagation started on the 26th at 8 p.m. Then it propagated from southeast to northwest at a speed at around 1 meter per second. Then I can say there is a change of Coulomb stress, that is, it triggered earthquakes on other structures, so transform fault and also other normal faults. Then the lava flow started. I'm not sure of when, but it started. It grew a bit. It reached a kind of stability until it then completely stopped in June. At this point, we have a kind of maybe collapse or maybe readjustment of stress, but this triggered some earthquakes. So that's the conclusions, the guesses we can make with hydrophones. And I think this shows that with only one type of sensor, we can do quite a lot of analysis, actually. So I think hydrophones are fantastic tools to monitor earthquakes and crises. And I would like to thank you for your attention. And as I like to take photos during my cruises, here are some. Thank you.
Thank you so very much. We're going to open it up to some questions. So Katie, any questions online? All right, for folks online, if you have anything for us, go ahead and put it into the chat box and we'll throw it over to the room. How about questions in the room?
Thank you, Pierre-Yves. That was wonderful, very interesting. The eruption you saw with the bathymetry and the pressure change, it's an amazing large volume. How did you get to that number? Were you subtracting bathymetric grids? I didn't really see a difference in the terrain there that you were suggesting.
Yeah, we used the common diachrone bathymetry. So we used the bathymetry grid of last year, the bathymetric grid of this year, and we can indeed just subtract each pixel of the resulting grid. So this gives a difference of 8 for each latitude, longitude pixel. And if you integrate that over the surface of eruption, you then can get an estimate of the volume. And regarding the mass, it's just an estimate of what could be the density of such rock, such basalt.
One quick follow-up. And so you have the speed of the magma intrusion, meter per second, and you have that volume. How do those rates and sizes compare to other sections of the Indian Ridge?
We yet don't really know because until now, most monitoring of such crises were done only with seismometers from land stations. And they are so far that it's very difficult to estimate such precise parameter, because to estimate this speed of 1 meter per second, we needed a high precision of location of T wave to see their propagation. And with distant stations, we would not be able to do that. So I think this is the first such result for the Southeast Indian Ridge.
Any other questions from the room? All right, give me just a sec.
Thank you. This slide kind of inspired me to ask this question. Did you, were you able to detect any differences in the behavior of the animals in response to the eruptions?
We don't know yet because it's making a lot of noise in the frequency bands used by large whales. So we could expect such change of behaviors, but as the data are quite recent, we only had them for 3 months now. We didn't do such quantification, but I think it's a good idea to try to analyze this. Yeah.
Nice. Any other questions? Katie, any questions online? All right, I think we're going to wrap up there. Why don't we give our speaker one more round of applause? All right, everyone, thanks for being here. Hope to see you next week, and thank you again very much.